Hi, this is the section 3.1, which is about derivatives of polynomials and exponential functions. So for that, we will define the derivative as the limit of difference quotient, and then interpret the derivative of a function at a point using also the concept of tangent line. Then recognize the derivative of basic functions, and finally apply the sum and difference rules of derivative. So the first thing is the link between the definition of derivative and the limit. So we saw in the previous chapter the concept of limit, and here we use it for defining the derivative. So the link between the derivative and the limit is the following, is given by this formula here. So you can see here, this formula is giving the derivative in terms of limit. So if I want to compute, if I have a function and I want to compute the derivative of f, which is f prime at the point A, then I will compute this quotient, okay, the limit of this quotient, f of x minus f of a over x minus a when x approaches a. Let me write it for a given point. Let's say I will compute f prime of 1. Then this is limit f of x minus f of 1 over x minus 1. And the limit is taken when x approaches 1. So if I compute here the difference between the y for x, the y for 1, divided by the difference of the x's, x minus 1, this quotient gives at the limit the derivative of f at the point 1. So this is a simple basic definition of the derivative linked to the limit. In fact, we will use more the rules of the derivative to compute the derivative, but also sometimes this is used to conclude some limits. Okay, so the other way is more used for this definition. It means that I can interpret or find some limits using the derivative. Okay, here again, it's interpretation of the derivative in terms of a tangent line. We know that the slope of the tangent line is given by the derivative f prime of a, because the change on y divided by the change of x, this is exactly the slope of the tangent line. Okay, here is an example. So find the equation of the tangent line to the curve y equal to x squared at the point 1, 1. So clearly, here we have the function f of x is equal to x squared. Okay, and if I want to find the tangent line, then it's of the form y minus the y of the given point, which is 1 here. So y minus 1 equal to the derivative of f at the point x, given x, which is 1 here, times the difference x minus 1. And I need just to compute f prime of 1. Okay, so here f prime of 1 is kind of a limit, and the computation is easy here to find it using the limit. However, later we will see that we have the rules for the derivative, and it can be simply computed by the rules. So here, f prime of 1, if we compute this limit, expand like that, then expand this square, 1 plus h squared, it's of the form a plus b squared, so it is equal to a squared plus 2ab plus b squared. Just do that, you obtain this, minus 1, then you simplify by 1 here, and you will get 2h plus h squared Then put h in factor. So h times 2 plus h and divided by h. That will give simplification by h, and you will get 2 plus h. Take the limit at h equal to 0. Then you substitute h by 0. You will get 2. Okay? So this is the f prime of 1 at the f prime of 1 equal to 2. Now, you can write you can write here the equation of the tangent line, as I wrote it before. This is the equation of the tangent line, y minus 1 equal to the derivative of f at 1 times x minus 1, or you can simply write it in the slope-intercept form like that by doing some computation. And here is the graph. You see that we have the x squared, the graph of x squared like that, and the tangent line, which is this one. Okay, so this is the tangent line. Okay. Now we continue with the definition of the derivative using the limits, and we can write, in fact, that this formula, the formula that we wrote before, can be extended to any number x, and for a fixed parameter h. If you remember, the previous formula is something like that. F prime of x is equal to limit f of x minus f of a over x minus a when x approaches a. The difference between this formula and this one is that here the limit, in the second one, the limit is changing depending, here is f prime of a. So the limit here is changing depending on the value of a. But with this new formula, whatever the a or the x that you take, the limit is computed all the time as h equal to 0. So maybe this second formula is much better than the first one, because we compute all the time the limit at h equal to 0. So next we will use more this formula than the first one, although the first one also is used sometimes to interpret some limits. Okay. Some notation for the derivative f prime of x can be denoted by df over dx, or if y equal to f of x, so it's dy over dx, sometimes y prime, and so on. Or we use also this notation or this one, but the most used will be this one, and this one. Okay, sometimes this one. So that's the definition that we use, and this is called this one is called the Leibniz notation. Higher derivative, it means when you have the first derivative, you can differentiate again and you obtain the second derivative. When you do another derivative, it will be third derivative, and so on. You can continue with the Leibniz notation like that. You precise the order of derivative, and also in the variable you put the variable power n. That means that you make the derivative with respect to x n times. Look at this theorem. If f is differentiable at a, then f is continuous at a. This means that the differentiability of the function is stronger than the continuity. So a function which has derivative, that means it is continuous. But the opposite is not true. You may have a continuous function, but not differentiable at a point. Okay, and we will see some examples for that. So here you see that this function is differentiable. So each time you have a tangent line which is well defined at any point here. But for the second one here, you have this problem of differentiability at the point A. Maybe the most also common example is the absolute value function, absolute of x, which the graph is something like that. Okay, so clearly there is problem at x equal to 0 here. We cannot have the derivative at the point 0. And here is, in fact, the example of absolute value. So clearly we will have f not differentiable at the point 0 using the concept of the limit. So we see here that when we replace the definition of prime of 0 is equal to limit h approaches 0 of f of 0 plus h minus f of 0 over h. That's the second definition that we use here. And when we replace this, because f of x is equal to absolute value of x, so we will get absolute value of h. Since f of 0 is 0, f of 0 plus h, that means f of h, and f of h is exactly equal to absolute value of h. So we will get this quotient, absolute value of h over h, and this quotient is equal to 1 when h is positive, and it is equal to -1 when h is negative. So we cannot have the limit. So right, left, they don't meet. 1 is not equal to -1, so the limit does not exist. And we say that the function is not differentiable at 0. So here you have an example of continuous function. The continuity is clear since when we graph the function, it is continuous here. We don't stop, so it's continuous, but we have this problem of differentiability at 0. So an example of f continuous, but it is not differentiable. However, if f is differentiable, then necessarily it will be continuous. Good. So look here at some special function, particular function, like the constant function. Okay. In fact, the constant function has a graph like that, which is horizontal line. So clearly, when you take the slope, the variation of this function, it is equal to 0, since the y is constant all the time for any point. So that means that the derivative is all the time equal to 0. So we say when we have a constant by itself, not multiplied by something, no, just plus c or minus c, then the derivative of this function is equal to 0. And that's from definition of the limit. Okay. Okay, so that's what we said before. And now we will go to other basic function like x power n, and we will compute using the limit. We start by the simple case n equal to 1. That means f of x will be equal to x. And in this case, if we compute using the limit, then we will find that the derivative is equal to 1. And now it's a rule. When you have x as function, derivative of x is equal to 1. And we will see a little more rule, a little more involved rule. That means the derivative of x power any number n fixed. Okay. So here it is. When we have x squared, derivative of x squared is equal to 2x, and derivative of x cubed is equal to 3x squared. So in fact, we have the general rule, which is this one. This is the proof. You don't need maybe to follow a lot this computation, but go directly to the power rule, which is this one. So in practice, when you have x power by a number n, whatever the n, it can be any real number. Okay, so when you want to make the derivative of this monomial, then what you do, you take the n here in front of the x. So it's n, then x, and the power here, you make it -1. Okay, so n -1. That's the derivative of x power n. Okay, so we'll use a lot this formula of derivative of x power n to compute some other basic function. Let me here. So as examples, when we have x power 6, so the derivative is x power 6 prime derivative. That means we take the 6 in front, then x power 6 minus 1, that means 5. I will write some details in the first example, then it will be faster later. If we want to differentiate x power 1/1000, the derivative will be 1/1000, and x power 1/1000 minus 1, that means 999. And you can continue to play with these examples like that. However, when the power is not an integer or a natural number like that, still this formula can work. We will see it later. Okay, so here it is, the general version. So if you take any real number r, you compute the derivative of x power r, then you do the same thing. Take the r in front of the x, then make the power -1 and compute. So that's the rule. So for example, if you have x power pi derivative, that means it is pi x power pi -1. That's an example that you can work on. Of course, here you must have the variable x here to make this derivative. If it is a number here, then it's like a constant. So be careful when we have something like that. For example, 2 power pi. Okay, there is no variable x, so the derivative of this is equal to 0. You don't apply any formula. This formula works when we have variable x here and a power that does not contain x. So it's something like that. Okay, x power a number r. So the variable is here, the number is here. Okay, so the derivative of this is r x r -1. Okay, good. So another example here, which is easy. Sometimes this is a good example, and we may use this idea to another function, to other functions, sorry. 1/x², in fact, you can write it like x power a number. That's the first step that you do. So x power -2. Then you do the derivative. So the derivative f prime of x will be, as usual, this is your number r. Okay, so apply the formula here. So it's -2x -2 -1. -2 -1, it will be -3. And here, be careful of the computation. Don't make error or mistakes in the computation of the power. So the power -1. The power, it is -2 -2 -1, that gives -3. So we say that the derivative of 1/x² is equal to -2x power -3, that we can write like that also, -2/x power 3. Okay. And by the way, you can apply also for fractional power or something like that. We will see some other examples. Like this one, you see here. So first, I will transform my function. That's the first step that you do. Okay, you put it like x power. Look at it. There is 2 in the power of x, but in the root, there is third square root. So it's like 1 over 3. So it's 2 over 3. And then do the derivative. So y prime is equal, this is your r. Apply the formula. So it's 2 over 3 x, 2 over 3. And here, since it is fraction, the -1, you will write it minus 3 over 3 directly to do the computation, okay? So it's like -1, but I write it with the same denominator as 2 over 3. So I will get 2 minus 3, which is -1 over 3. So my result will be 2 over 3 x power -1 over 3. You can write it with the positive power if you like this. So you can write something like that, 2 over 3 x power 1 over 3, that you can write also 2 over 3 cube root of x. Okay, all of them are the same, but the writing are different. Now, we worked on these examples, so we will go to what we call the normal line to a curve. So the normal line is something when you have a graph like that, you take the tangent line at the point. Let's say I will take this point here, okay? And I will draw the tangent line, which is something like that. This is the tangent line. So what is the normal? The normal is at the same point, a line which is passing by the same point, and it is perpendicular to the tangent line. So in fact, if you have the tangent, which is linked with the f prime of the point A, let's say this is A, okay? The normal line will be the slope of the normal line. You just flip the number in the slope of a tangent line and then put minus. So -1 over. Okay, so that's the slope of the normal line. And the normal line is easier sometimes to compute than the tangent line because you just, you have the derivative, find the slope of the normal line, and then the point. The point will be given by this point here. The plus b, the y-intercept will be given by the point. Okay, so we want here to find the equation of the tangent line and the normal line to the curve y equal to x root x at the point 1, 1. Okay. Here, the trick that we write our function like x power something. So y is equal to x power 1 times x power half. That means x power 3 over 2. And now the derivative will be easy because y prime will be 3 over 2 x power 3 over 2 minus 1, which is minus 2 over 2, so 1 over 2. Then apply this at the point x equal to 1. So y prime of 1 is equal to 3 over 2, 1 power half, that means 1. So y prime at 1 is equal to 3 over 2. Then my tangent line, I will not denote this by t. Its equation is y minus the y of the point, so -1, equal to the derivative 3 over 2 times, between parentheses, x minus the point 1. You can write this by multiplying this equation by 2. Then you will get 2y minus 2 equal to 3x minus 3. That you can write 3x minus 2y, sorry, equal to 1. So that's the equation of the tangent line. Okay, No, the normal line, since we find here the derivative is 3 over 2, so the slope of the normal line is slope of the normal line is equal. You flip the derivative, so it's 2 over 3, and you add minus. This is the slope. So it will give the equation like that. Y equal to minus 2 over 3x plus a number b that is the y-intercept. How to find b? Replace the point here in the equation. So we will get 1 is equal to minus 2 over 3 times 1 plus b. To solve this equation, multiply everything by 3. So you will get 3 equal to minus 2 plus 3b. That means 3b is equal to 5. And that means that b is equal to 5 over 3, and you are done. You have the equation here of the normal line. Here the b. And here is the graph of this function. Now we will go to the rules of derivative. If you have a function multiplied by a constant, then you can take the constant outside of the derivative. Okay, like for example, you do 2x derivative. The constant can go out, so it's 2, and derivative of x, which is 1, so 2 times 1 and equal to 2. That's an example of this formula. Here another other examples. So if you have 3x4, you take the 3 outside, because here the constant is multiplied by a function of x. That's why we take it out of the derivative. And then you have to do the derivative of x4. This is the formula of the power. Then you will get 4x cubed multiplied by 3. So it's 12x cubed. Same thing here. If you have minus x, you take the minus 1 outside and you differentiate the x, which is the derivative is equal to 1. Then you find minus 1. That's very easy. You have also the rule of the sum. If you have sum of two functions, then you can separate the derivative like that and like. Don't mix it with the product later that we will see. So far, multiplication by constant, sum, difference, they are easy. Just separate the function, okay? We will see the product and the quotient later. Look at this, we can write it like that, even with 3 functions. And the difference also, same thing, you can separate the function. It means that if you have, for example, x squared minus x derivative, you can write it x squared derivative minus x derivative. And just compute, this is 2x and this is minus 1. That's it. Look at this example also, we have sum and difference of many monomials here. So we can separate each one. So we start with this one, then this one, and so on, okay? So the derivative of this will be 8x7 plus 12 times 5, that's 60, x power 5 minus 1, that's 4. Then minus 4 times 4, that's minus 16, x power 4 minus 1, that's 3. And then you continue, 10 times 3, 30, x squared, and then minus 6, and the derivative of 5 is 0. So that's the answer. Okay, you have this try and check, differentiate the following functions. So we have this first function. It's better sometimes to write it in a simple form, like that you don't do mistake for the function, okay? So for now, depending on the formula that we have, we will use the power formula. That means x, we separate x power 5 over 2 power 5, okay? So these over 2 power 5, this is like a c, a constant. So I will take it outside. So the derivative of this is equal to 1 over 2 power 5. That's my constant c. And then derivative of x power 5. That means 1 over 2 power 5, 5x power 4. And that's my final answer. Okay. The second function, 2i, g prime of x. First, I will transform a little bit the function g of x. Like that, I make easier the derivative of g. So g of x is equal to x times root x, but this equal to x power 3 over 2, because this is power 1, and this is like x half. So 1 plus half, this is 3 over 2. Then the second one, you see here, you have x squared times root x. X squared times root x, that means x squared x half. Make the sum of these, so x power 5 over 2, but it is in the denominator, so it will be x power minus 5 over 2. Now you can do the derivative. So g prime of x is equal to 3 over 2 x 3 over 2 minus 2 over 2, that means 1 over 2, and minus 5 over 2 x power minus 5 over 2 minus 2 over 2, that means minus 7 over 2. And this is the final answer. If we want to let the function like that, sometimes we ask to put positive power, so just make this in the denominator. That's it. Okay, the last one is h of x. So h of x, first I will transform the function before doing the derivative. So it's a plus b, but over x squared, that means multiplied by x power minus 2. And plus c over x, that means plus c x power minus 1. In this way, I can make the derivative easily. So h prime is equal to, this is constant, so this is 0. Then plus, and the power, minus 2 times b times x, minus 2 minus 1, that means minus 3. Then plus c times minus 1, that means minus c. X power minus 1, that means x power minus 2. And we are done, and we can write our derivative like that. Minus 2b over x cubed minus c over x squared. Okay. Now, the next part is the exponential functions. You know that the exponential function take the form of number a, which is positive a power x, sorry. Okay, so it's of the form a power x, and we want to find the derivative of this function, and it will be a rule. Just follow this computation in the limit, and the rule is that the derivative of a power x, I will go forward to the rule. So f prime of x is equal to a of x, f prime of 0. But what is f prime of 0? We computed this f prime of 0. So it is equal to 1. So here, in the case of exponential, when the base is e, we know that the derivative is f prime of 0 is equal to 1. So we have this this formula. The number e is linked to this limit, and we find that e is given such that the limit of h minus 1 over h, when h approaches 0, is equal to 1. That's the number e. So here we will use the fact that the derivative of ax here the formula that we wrote before. The derivative of ax is equal to ax f prime of 0. So it's linked to just to know the f prime of 0 for the function f of x equal to a power x. And here be careful of the exponential function because the variable x is in the exponent. It's not like x power a. That's different. Okay, this is not exponential function. This is like power of x. Good. So you see here, remember, of course, the graph of the exponential function when we have the ex function or any other exponential function like 2 power x, 3 power x, and so on. Okay, so here we have the formula for ex. The derivative of ex is equal to itself ex. But if we have another base, then be careful of the base. Okay, so this is only for the base a equal to e. So we will apply this, but by the way, we use a lot the natural exponential ex as functions, and also logarithmic natural logarithm ln. The inverse of this is ln of x. We will see it later. So these two functions are widely used in analysis of functions, but it's better to recognize or to recall the other exponential functions like base 2 or 3 or whatever. Okay. So here we will use the derivative, the rule of the derivative of ex to compute the first derivative f prime or f second to this function f of x here. So it's easy here to compute because we have the difference formula for the difference. And we know that d over dx of ex, it's ex itself. And derivative of x is equal to 1. So the first derivative is equal to ex minus 1. Now, to compute the second derivative, we start from here, from the first derivative, and then we make the other derivative. So again here, d over dx ex is equal to ex, but d over dx of 1, this is 0. So it is equal to ex. And starting from this order, if we want to compute the third derivative of f, it will be all the time ex. So fourth also the same, fifth the same. It will be all the time ex starting from the order 3. Okay, here is the solution of f and f prime, the graph of f and f prime. Okay, now we will go to section 3.2, which is the product and the quotient rules for the derivative. And these are very important. So if we have a product of two functions and we want to make the derivative of the product, so we have the formula. Don't make this mistake. This is wrong, of course. We need to alternate derivative and not derivative, okay, in the formula. We'll see it. Here it is. So if you have a product f times g and we want to make the derivative, first you can take the function f and make the derivative of the other one, and then switch the other one without derivative, this one with derivative, okay? As application, we'll see this example. We have here product of two functions, and we want to compute the derivative of f. So it's x derivative, the one of them derivative, times the other without derivative, and then plus the first one without derivative times the second one derivative. and the derivative of x is equal to 1. So 1 times ex plus x times derivative of ex is itself. Same thing, ex. So I can here write ex as common factor, 1 plus x, and this is my derivative. Okay, so if we want to compute the second derivative of this function, we continue to differentiate the previous function that we obtained, which is x plus 1 ex here. So the derivative of this function, again, we apply the product rule, and we see that here the derivative of ex is the same, but the derivative of x plus 1 is equal to 1. So here 1, and x plus 1 times ex plus ex times 1. So we will find x plus 2 times ex when we put common factor ex. If we continue the higher order derivative, then we'll find f third is equal to x plus 3 ex, and we can conjecture that f power n, the derivative of order n, is equal to x plus n times ex. So each time you see the 3 here is the same as here. The 2 here is the same as here. The 4th is the same as here. So we can conjecture that the n must be n here. And that's the formula for n derivative. Now the quotient rule, it means when we have to differentiate f over g, first thing that you make the square the denominator, and then in the numerator we will put a formula similar to the product rule, but with minus here. Be careful of this, okay? So we apply this formula in this example. So y prime here is equal to, first thing, the denominator squared, x cubed plus 6 squared, and let it like that. Don't expand the denominator. However, in the numerator, this is the function f, this is the function g. So I will start with f prime, okay? F prime is equal to 2x plus 1 times the g without derivative. So x cubed plus 6 minus x squared plus x plus 2, that's minus 2, that's f, times the derivative of g, which is 3x squared. Now we expand just the numerator. So we keep the denominator like that, squared, and we expand the numerator, so we will get 2x fourth plus 12x plus x cubed plus 6, and then we expand, but there is minus here in front of the expansion. So minus 3x fourth minus 3x cubed and plus 6x squared. Now we start with the highest monomial, which is x fourth in the numerator. So I will get this with this. Then 2 minus 3 is minus 1. So minus x fourth. Then x cubed with x cubed. So 1 minus 3, that's minus 2 x cubed. And then the x squared, which is here. So plus 6x squared. The x here, plus 12x, and then last one, the constant, plus 6. And that's it. You let your derivative like that. Okay, we'll end this part by the try and check examples. So the first thing, I will compute the derivative of x plus 2 over x minus 1. I will use for that the whiteboard. So here is the whiteboard. Then my function is f of x equal to x plus 2 over x minus 1. So this is the quotient rule, and my derivative will be equal to over x minus 1 squared. And then in the numerator, 1 times x minus 1 minus 1 times x plus 2. So in total, I will have x minus 1 minus x minus 2 over x minus 1 squared. That means when we simplify by x, minus 3 over x minus 1 squared. And the second example, which is g of x equal to, so this is I to I, x plus root x times x minus x cubed. Okay, so here we can apply the product rule. We can also expand the function and compute easily the derivative. It's up to you, up to the choices in the MCQ question. If it is an MCQ, then here I will choose to expand the expression of the function. So I will get x squared minus x4 plus x power 3 over 2 minus x 3 plus half. That means 7 over 2. Now I will differentiate g prime of x equal to 2x minus 4x cubed plus 3 over 2x half minus 7 over 2 x 7 over 2 minus 1, that means minus 2 over 2, so 5 over 2. That's the derivative of g. Now, the third one, which is h of x equal to x squared plus 4x plus 1 over x root x. And here I will again change the form of the function to make it easier to compute the derivative. So here I will take advantage that there is no sum or difference in the denominator. So I can write it x squared plus 4x plus 1 over x power 3 over 2. Okay, so then I will separate the numerators. So it will be x squared over x 3 over 2 plus 4x over x 3 over 2 plus 1 over x 3 over 2. Then I will write all these power of x. Each term power of x. So x power 2 over x power 3 over 2. So x power half. Plus 4 x power 1 minus 3 over 2. So minus half. And plus x power minus 3 over 2. Now I can make the derivative easily. H prime using the power rule formula. So it's 1 over 2 x power half minus 1 minus, so that's minus half, plus 4 times minus half, that's minus 2, times x minus half minus 1, minus 3 over 2. Then the last one, minus 3 over 2, that's the r. If you remember, this is the r. Then x power r minus 1, that means minus 3 over 2 minus 1, that's minus 5 over 2. and we are done for the derivative of h. Now, the next example, k of x equal to x over x plus ex. You see here that the quotient in the denominator has sum or difference, so I cannot make a change to the expression, and here I am obliged to work with the, in some sense, to work with the quotient rule. So k prime will be the denominator squared, x plus ex squared, and the numerator f prime g minus j prime f. So 1 times x plus ex minus x times the derivative of this function, which is 1 plus ex. Okay, now I will expand the numerator. I keep the denominator as is. So x plus ex minus x minus x ex. There is simplification by x, and I can put ex common factor. So ex 1 minus x over x plus ex squared. I can stop here for the derivative. The last example here is question number 2. Find, if we have y equal to 1 over x squared plus 1, then find the third derivative of this function. We will start, maybe we do the first and the second, and that's enough, okay? So I can transform my function like that. Well, let me, since it is sum, I will put it like that. So it's y prime is equal to x squared plus 1 squared. And then in the numerator, I will have the derivative of 1, which is 0. So 0 times anything is 0, then minus 1 times the derivative of x squared plus 1, that is 2x. So in total, I will have minus 2x over x squared plus 1 squared. Now I will go to the second derivative. So again, quotient rule. Okay, so I will have x squared plus 1 power 4. And in the numerator, the derivative of minus 2x is equal to minus 2 times the function in the denominator as is. Then I will make the derivative of, so there is minus, then minus 2x times the derivative of x squared plus 1 squared derivative, okay? And this quantity needs more attention. Look, this one, I will compute it here. So in fact, x squared plus 1 squared prime. Before doing the prime, I will expand, since I don't have here something that we will see later, which is the chain rule. Then I will use the basic computation without using the chain rule, which is not known at this step here, at this level. So I will expand x squared plus 1 squared. That will give me x4 plus 2x squared plus 1. And this is derivative of all this. So I will get 4x cubed plus 4x and plus 0. So that's it for the derivative. This quantity, I will plug it here again in this place, and I will get my y second. Okay, so y second will be equal to x squared plus 1 power 4, and in the numerator, so minus 2 x squared plus 1 squared. Okay, and I will expand this square. So it is equal to minus 2 x4 plus 2x squared plus 1. Then there is minus minus, so it will be plus 2x times the quantity that we compute here. So 4x cubed plus 4x. Okay, so in final, I will get the denominator again, and minus 2x fourth, minus 4x squared, minus 2, plus 8x fourth, plus 8x squared. Now put the like terms together. So x fourth, I have these and these, so it's 6x fourth. X squared, I have this and this, so it's plus 4x squared and minus 2, and that is the y second here. I will not go to the y third since the computation will be harder, and since we don't have at this level, we don't have the chain rule or any other rule that we can have that can help here, that can help. So I will stop to y second, and by that we let me go back to, I think this is the last example. Here just share the last part of this lecture is just a remainder of the formula. So just recall this. And this is the end of lecture 3.1 and 3.2. Thank you so much.